Okay, section 10.3 is on polar functions. So we're going to talk first about polar coordinates and rectangular coordinates. So if we have a graph like this, and we have a point at root 3 over 2, comma 1/2, this point should look familiar to you. It is a point on the unit circle, so a radius of 1, where the angle measure is pi over 6. So this point is a rectangular coordinate. So root 3 over 2, comma 1/2. Rectangular coordinates are in terms of xy. If I want to write this as a polar, I could spell right, as a polar coordinate, I would measure by the radius, how far it is out from the center, and what angle it is. So it's at a pi over 6 angle, out 1 unit, and that's exactly the same spot on the graph as root 3 over 2, 1/2. This is in terms of r and theta. Let's look at another one. So if I have a point out here at pi over 4 with a radius of 2 root 2, can we change this polar coordinate, which is 2 root 2 comma pi over 4, into a rectangular coordinate? So I can use the fact that this is a isosceles triangle. Pi over 4, remember, is on the line where x equals y. So these two values are the same. So we can say a squared plus a squared equals 2 root 2 squared using Pythagorean. And that would be 4 times 2, dividing both sides by 2, we get a equals 2. So this is the ordered pair 2 comma 2 in rectangular coordinates. We're going to see another way to do that in a little bit as well. So let's see what we can do with a couple of these problems. So find rectangular coordinates for the point with the polar coordinate 4 pi over 2. So I'm going to go around pi over 2 units, and I'm going to go as a radius of 4. So it's pretty easy to see by the graph we drew that this is just the point 0, 4. Find two different sets of polar coordinates for the point with the rectangular coordinates of -3, 3. So again, this is on the line y equals x, or y equals -x, and it's out, it's over 3 and up 3 units, so I should be able to find the distance from the origin. So that would be found at -3 squared plus 3 squared and take the square root. So that's root 18, or, is that right? 9 plus 9 is 18, yep. So that's 3 root 2. And the angle measure I should know as 3 pi over 4. So this is 3 root 2, comma, 3 pi over 4. So that's moving from rectangular to polar and back again. Now we're going to do some other work with converting from rectangular to polar. So these 4 conversions are ones that we are going to use. X equals r cos theta, y equals r sine theta, x squared plus y squared equals r squared, and tan theta is y over x. So let's take a look at how we're going to use these. So first of all, oh, I should have done a blank screen earlier. Hold on. Yeah, let me back up. Sorry, you'll be able to squeeze this in, I think. If not, just put a little arrow that this should have gone back up here. Sorry about that. So if I want to graph polar coordinates, let's say I want to graph r equals 2. This is just the set of all values. There is no theta here. all values 2 units out from the center. And I hope you can see that this is just going to form a circle. What if we have r equals -3? Well, no matter what my theta is, if you remember graphing polar coordinates before, which I hope you did, all -3 means that instead of going towards the angle measure, I go away, but I'm still going 3 units. So it's still going to be a circle, this time with a radius of 3. If I want to graph theta equals pi over 6, I want all points that are on the line that is pi over 6 units from the origin. Okay, so just some examples there. Sorry about that. Back to this. Let's look at this now. So if I want to do some conversions here, let's say I want to convert r equals 4 sine theta to a rectangular coordinate. So I want you to think for a minute about some of the conversions that we had a little bit ago and what we might be able to do to change this to a rectangular equation. R equals 4 sine theta. So if I can get r squared, I can change that to x squared plus y squared. My problem is that I'm not sure what I could do if I squared both sides. Don't write this down. I'm not sure what I could do with that sine squared theta. I didn't have a conversion for that. So the other way to get r squared is to multiply both sides by r. So I'm going to write this as r squared equals, if I multiply this by r as well, I can write it as 4r sine theta. R squared is x squared plus y squared. R sine theta is y. So there's my xy equation. I'm going to clean it up. X squared plus y squared minus 4y equals 0. Do you remember doing complete the square to create conic equations? So completing the square, I take -4 over 2 squared. That's the value that's going to go in the end spot. Then I can take this and factor it. Whoops, I need a plus sign there. And now if I look at this, I can see that it is a circle centered at 0, 2 with a radius of 4. Okay? So that's converting. We'll do some practice with that together. Parametric equations of polar curves. Now we're combining our parametrics and our polars. If r is a function of theta, I can define it parametrically by using my conversion x equals r cos theta. Since f prime of theta is r, whatever this function is would go in front of the cos. And since y equals r sine theta, r could be replaced with this function times sine theta. So let's take a look at one and see what we can do with this. And we're going to use this. So if I want to change r equals 6, r equals sine of 6 theta to parametrics. So x is r cos theta. R, from my definition, is sine of 6 theta cos theta. And y is r sine theta. So y is going to be the sine of 6 theta cos theta. Now when we get to class, we're going to look at graphing this equation both in its polar form and in its parametric form. We'll do that when we're in class together. All right, finding slope of a polar curve. So if I want the slope of a rose curve, we'll talk about what a rose curve is later. R equals 2 sine 3 theta at the point where theta is pi over 6. So a rose curve looks like this. This is the graph of this equation. And there's the point pi over 6. So if I went up pi over 6, that's my point. And I want a tangent line at that point. To get a tangent line, I need dy dx. So the first thing I want to do is put this into parametrics. So x equals, again, r cos theta. So in this case, r is 2 sine 3 theta. So 2 sine of 3 theta. And again, that's all r. And x is r cos theta. Y is r, substitute in. Y is r, that's my r value, sine theta. So there are two values in terms of x and y. So to get to y dx, I'm first going to get dx d theta and dy d theta. So just like we did with our parametrics when we were in terms of t, if I then put dy d theta over dx d theta, I will get dy dx. All right, so dx d theta is going to be, and actually I think I'm going to start on a clean slate. Okay, so x equals 2 sine 3 theta cos theta, and y equals 2 sine 3 theta, whoops, not what I wanted to do, 3 theta sine theta. There we go. All right. Actually, I just saw that. Well, I'm going to keep going. So dx d theta, product rule. The derivative of the first would be 2 times the cos of 3 theta times 3. Derivative of the first times the second plus the first times the derivative of the second. So I also need dx d theta evaluated at pi over 6. So that's going to be 6 times the cos of pi over 2 times the cos of pi over 6 plus, actually I'm going to change this to a minus sign, bring that minus forward, 2 times the sine of pi over 2 times the sine, why does it keep doing that, times the sine of pi over 6. Evaluating this, I get 6 times 0, none of the rest of that matters, minus 2 times 1 times negative, times 1/2. So this whole side equals negative 1. Let's do our dy d theta. So again, the derivative of the first is 6 cos of 3 theta times the second plus the first times the derivative of the second. Evaluating at pi over 6, this is where I want to find my slope. I've got 6 times the cos of pi over 2 times the first times the second. Something's wrong. No, that's right. Times the sine of theta plus 2 times the sine of pi over 2 times the cos of pi over 6. Okay? So now I've got 6. The cos of pi over 2 again is 0, so this whole first piece goes away. I have 2 times 1 times root 3 over 2, which equals root 3. So write all that down because I noticed that my slide is messed up. So I'm going to have to erase this. So make sure it's written. You can go back to it if you need to. So here we are. dy dx is dy d theta over dx d theta, which is d d theta of y over d d theta of x. We did all that work a minute ago. And what I get when I evaluate pi over 6 is root 3 over negative 1, which is negative root 3. So that's the slope of the rose petal that was defined on the last slide. Okay, area. The area of the region between the origin and the curve, r equals a function of theta, where theta between alpha and beta is the area, or the integral from a to b, of 1/2 r squared, should sound familiar, d theta. So again, that's our function, and since r is defined as a function of theta, that's what we're going to use. So here's what we're talking about. If I have a curve similar to one of the ones we've already looked at, and I want to evaluate this or find the area from 0 to pi over 4, what I'm doing is I'm taking little slices of area from the origin until I get to the pi over 4 slice. Okay, so let's try one. Find the area of the region of the plane enclosed by the cardioid. And a cardioid is another kind of polar graph. It looks like this, and it's defined by 2 times 1 plus cos theta. Any point on this cardioid is arc theta again, and we're going to do theta from 0 all the way, well, from 0 to 2 pi. So that'll give us the area as I take these thin little wedges, filling up the cardioid all the way around until I get back to the beginning. All right, let's take a look and see what we need to do. So we're going to take the integral from 0 to pi over 4. Oops, excuse me, pi over 4 was the last one. To 2 pi of 1/2 r squared. This is r. So 2 times 1 plus cos theta squared d theta. Integral from 0 to 2 pi. I'm going to have to square all this. So 1/2 times 4 times, if I square that binomial, I get 1 plus 2 cos theta plus cos squared theta d theta. I'm going to leave the 2. Usually I pull it out, but I'm going to leave it there for a minute. 1/2 times 4 is 2. And I'm going to use a substitution. These are in the first appendix for cos squared. 1 plus 2 cos theta plus 1 plus cos 2 theta over 2. Okay? So now you can see why I saved that 2. 0 to 2 pi, if I distribute, 2 plus 4 cos theta plus 1 plus cos of 2 theta d theta. I'm going to a new screen, so pause if you need to. So I left off at the integral from 0 to 2 pi, combining like terms, the 2 and the 1 together. I'm going to get 3 plus 4 cos theta plus cos of 2 theta d theta. All right, the book did not show a lot of the in-between work, but it did finish this off for us. So this is where we are right here. Taking the antiderivative from 0 to 2 pi, we get 6 pi minus 0, which is 6 pi. So that's the area, or doing integrals with polar coordinates. The last thing we're going to look at is the area between polar curves, very similar to when we did it between other curves. we're going to take 1/2 of the second function minus half of the first. So it's r sub 2 squared minus r sub 1 squared. So a very similar formula to what we've done in the past. Let's do one of these together. So we're going to find the area inside the curve r equals 1 and outside the curve r equals 1 minus cos theta. R equals 1 is a circle with a radius of 1. This is a cardioid, and it looks like this. They meet here at 1, 0, 1, comes all the way around, meets again, and comes back in. So I want inside the circle, but outside the cardioid. That means I want this area here. I'm going to go from negative pi over 2 to pi over 2. So area is the integral from negative pi over 2 to pi over 2. Whoops. 1/2 of my first radius, my bigger one, that's 1 squared, minus my 1 minus cos theta squared d theta. Now, looking at this, this is symmetrical, so I could eliminate having to go from negative pi over 2 to pi over 2 by taking twice the integral from 0 to pi over 2. And that'll give me a little bit of leeway, make things a little bit easier. And it will allow me to eliminate these two values. So the integral from 0 to pi over 2 of 1 minus, again, squaring my binomial, 1 minus 2 cos theta plus cos squared theta d theta, integral from 0 to pi over 2, 1 minus 1 is 0. All these signs will change because of the negative in front. 2 cos theta minus cos squared theta d theta. And this one I'm just going to stick in my calculator to save us a little time, and that's approximately 1.25 units. So that's all the notes. I do want to show you one other thing. This is a compilation of a whole bunch of different polar equations that we normally work with. It is in your book, so you'll be able to use that whenever you want. So we have circles, ones with centered at 0, ones that are above the x-axis, one to the right of the y-axis, depending upon what values we have. These are our Rose curves. Depending upon whether this number is odd or even, the Rose curves look different ways. Symmetry is different. They have different numbers of petals. So again, by looking at any function that looks like this, any of these, you can tell what the function or the graph will look like. And then we have the limicons, and these are a plus or minus b sine theta or a plus or minus b cos theta. We've done a couple of those. We did a cardioid. There's also one called a loop, a dimple, and a convex where it just flattens a little bit here on the side. And lemniscate curves come from a function that looks like this. And then the spiral of Archimedes, and that's just crazy. So that's it for the notes. Again, those last pages, they're in your book. You'll be able to use your textbook for everything you need, and we will work some more with this in class.